Welcome everyone. My name is Vijay Natarajan. It's a pleasure to welcome you all to this talk by Professor Ingrid Hotz. Ingrid is the first Dr. Ramkumar IISc Distinguished Chair Professor. She's been in IISc for the past 1 month. She's going to continue and stay with us for another month, interacting with several faculty, several research groups within the institute and also outside. I would like to invite Nandri to first talk a little bit about the chair position before I introduce the speaker.
Thank you very much, Vijay, and a very warm welcome to you. So it's a matter of great delight that there are 2 distinguished chair positions which have been instituted at IISc by Professor Rakesh Agarwal. As many of you may already know, Professor Agarwal is widely regarded as the father of data mining, and he has written a very large number of highly influential papers in the general areas of data mining, information retrieval, and so on. And he himself was a Srimati Rukmini Sri Gopalakrishna Chair Professor at the Department of CSA on 2 separate occasions earlier. So, because he came to the institute on a chair position, and he was very impressed by the way this chair position itself is helping the institute. So he himself wanted to institute 2 chair professorships, one in the name of his father, Professor Ramkumar, and another in the name of his mother, Mrs. Urmila Agarwal. And he said that we're very fortunate that the first chair position is exclusive to our division, the IISc division. And it's a matter of great delight that the first chair position has come to the CSA department. And it's a matter of even more delight that Ingrid Hotz is our first Professor Ramkumar Chair Professor. The Professor Urmila Agarwal Chair Professorship is actually for women researchers who could be working in any of the areas of relevance to the institute. And I hear that the first Urmila Agarwal Chair Professor also is going to be here very soon. And so that way, I think, in some sense, this lecture is going to be a milestone. So this is the very first lecture that will be given by the Professor Ramkumar Chair Professor. So very warm welcome to you. And I'm sure your talk is going to be a visual delight. We are already able to see the first slide, which is so beautiful. So thank you very much. And let's welcome Professor with a wide applause.
Thank you. So thanks again to Dr. Rakesh Agarwal for instituting this chair professorship. And it's great to have Ingrid here. Ingrid is a professor at Linkoping University, where she heads a very broad and productive group on scientific visualization. Ingrid has held several positions in academia, in national labs. She was leading a junior research group under the prestigious Emmy Noether program in Germany prior to her position now at Linkoping. She's a leader in the field of visualization. She has actually chaired the premier conference in the area, IISc visualization, also Euroviz, another premier conference. She has been the associate editor of the key journals in the area, IISc Transactions on Visualization, Graphics, Computers and Graphics, and so on. She has also played an important role in nurturing certain key research areas, for example, topology and visualization. She has chaired the steering committee that has fostered research in this particular sub-branch of visualization. Ingrid has interests across the entire span of visualization. and has worked on several applications of visualization, including in chemistry, as you can see here, more recently, but in the past in medicine, in climate science, in material science, and many others, biology. Close to the topic of today's talk is her kind of close interaction with domain scientists, where she has brought to bear a lot of the visualization techniques that she has developed in flow visualization, in tensor visualization, scalar field visualization, towards solving real challenging problems in the domain. Right? So it's going to be an interesting experience to listen to what she has to say about how to work together with a domain scientist to develop visualization techniques. So really analysis with human in the loop. Welcome, Ingrid, and look forward to your talk.
Thank you very much. So I can skip over my talk now, since already has been said already. So thank you for the very kind introduction. But I also want to take this opportunity to thank everybody who was involved, that I got the possibility to come here. And I already met a lot of interesting people. I had a lot of interesting conversation with faculty, with students, and so on. And it's really a pleasure to be here. And I'm very, very honored to have the possibility to be the first to take this position here. So in the following in my talk, I will give an overview about recent work with a strong emphasis on the interaction with the domain scientists. So if I'm not here, so then normally I would work. What should I do?
Yeah, maybe pushed up a little bit. Yeah, I think somehow it's not catching.
So is it better now? Can you hear me? Actually, also online, if there's somebody who can't hear, just let me know in some way. So normally I'm working in Sweden, in a city called Norrköping, a little bit south from Stockholm. And it's a very small city, but it's still a very good place to do visualization, since we have kind of basically under one roof all aspects of visualization, with a big research team just consisting of 7 faculty. But we also have an interaction with the public there, so that we have an associated museum in these spaces where we can apply part of our research to communicate science to the general public. And we also have a dome theater, which is available to us to showcase scientific stories here. So concerning myself, so within all this broad spectrum of visualization, I'm mostly funded by something that is called the Swedish eScience Research Center, which is specific for funding research questions that are on the one hand side really deeply in something that they call e-science, which would be HPC, all kind of data analysis, but also visualization. And on the other hand side, more in classical science, like physics, chemistry, but also medicine, brain sciences, climate sciences, just to give some examples. And in this context, I'm really interested in data analysis with a goal to help people to understand their data. This means if I say it's human in the loop, I mostly mean it's a scientist in the loop being really a part of the entire process of the development of visualization methods. And this also means that our work is very application driven, but also has a big component of method development. Just to give you an overview of some applications that we are mostly dealing with, this is the first class of novel materials, I call it in summary, and this ranges from molecular simulations, really from the very, very small scale, but goes up to mechanical engineering and even the automotive industry. We have a lot of applications in the medical environment, where workflows play an important role, where visualization can kind of make the data analysis process much more fast and efficient, with the goal of hypothesis development and formation. And a last part, which actually is a part of my research since my beginning, is understanding of turbulence, which is related to flow simulations, where again, I'm very much involved in these small scale questions, looking at individual vortices, thinking about how the vortices connect, but on the other hand side also in huge simulations, producing huge data sets, like for climate simulation and considering entire ensembles. From a method point of view, I'm interested in combining automatic methods with explorative methods. And here, hierarchical abstractions play an important role that for sure have to fit to the application, track structural changes. Thereby, we often apply topological methods, just using concepts from this area, which have been proven very powerful in the context with visualization. And last and not least, exploration and interaction is an essential part of our work. So in the following, I will go through a couple of applications of our work. I will start with a view from the application for the first half of my talk. And for the second half of my talk, I would rather focus on one specific technology development that we have done over the time. I will see how far I get. Maybe you only get the applications. If I don't, I'm not fast enough, but we will see. So the first application that I've chosen is within molecular dynamics. What you can see here is a simulation of a docking process. You have one big molecule in the center, and then you have a lot of probes that are swirling around, and these simulations are running for a very long time. And you see already that some of these molecules tend to dock onto this large molecule, but really to understand what is the mechanism of this docking and where does this docking happen is really a time-consuming analysis task. And with this example, I also talk a little bit about the history of collaboration. So in the beginning, when you start a collaboration, often the first step is really to get to know each other. I have to understand what is the data, what are the questions, and they have to understand actually what can visualization do. And often the first steps is just to analyze what do people typically do. And our first step here was kind of to develop an integrated framework that will combine a lot of these different tasks that they have been doing using a lot of different tools, switching from here to there, a tedious thing, a time-consuming thing, just providing an interactive framework where all this comes together. And this is a lot of statistical representations. Here we have timelines of selected properties shown over the entire simulation. Here we have some aggregated statistics measurements of selected properties. And in the center, we have a spatial visualization of the molecules. This is just one example. There are many different spatial representations available here. And something that you can observe very often, that just providing such an interactive framework immediately inspires novel research questions. I think something that is really important is to give people the possibility to filter, to aggregate, and to just go back and forth from between different views. And the first thing that came here up as a novel request was that probably traditional properties that they're looking at are not sufficient to understand what they want. And the first add-on was a tool where you can easily define some properties yourself by clicking, but also by text commands and some operators which made it easier to define the properties. This could be, for example, certain angles that are very typical for a conformation of a molecule. This also could be certain distances. This could be defined on one specific molecule, but it could also be defined on many copies of these molecules over an entire ensemble. And then we automatically try to derive these properties from the entire data set. And here we get then a representation of the temporal development of these properties as a distribution here. For example, if I look at such an angle, you will see it in many copies of these atoms, and then you see how this develops over time. And in all of these tasks, one thing has a very high priority is to be efficient, to be fast, to be quick. If somebody has to wait half an hour for this representation, people will not do it. So depending on the size of the data sets, which can be large, this can maybe take 1 or 2 seconds but this is still something that is acceptable. And in many cases, I think I would say the visualization has to keep path with the way of the reasoning of the person who is looking at these visualizations. I look at it, I spot something, I have a new question I want to ask, I want to filter, I want to get immediate response from my data set. Another thing that also came out that is very important to be able to select substructures, and we have been working a lot on finding ways here. So we have kind of two of these structures selected to give a nice interface to select structures. And again, we have selection just by picking, drawing. We have crowing operations, which are can be very domain specific, given to restricted to certain substructures. We have cloning to other molecules, and we also have, again, text queries, which turn out over the entire process that these text queries are really, really essential for this user group. For other user groups, this might not work, but chemists are used to scripting and using some kind of programming language to interact with the data.
So you had a very basic question.
Sure.
Very naive question. For example, for exactly the input we are giving.
So here in this case, so this is output from a chemical simulation, and there are kind of different data formats. We call this kind of a trajectory. And for this specific data set, you get kind of information of the location of all the molecules. You get the identity of the molecules, kind of what type of molecule is it. That's something that we need here, for example, red is always oxygen, and then you can immediately kind of spot what kind of molecules are there. But then sometimes there are also additional information about these molecules. But here in this case, so this geometric location is very essential. We have some fundamental knowledge that is also communicated about typical bondings, about typical sizes of molecules, but which are in the end somehow incorporated in the tool. The tool already knows kind of a typical extent of an oxygen atom is the size, and so on. But depending on the application, it can look very differently. This is often a very important step in this entire collaboration process, is that we understand the data format. Often there's a lot of transformation to formats that we can read in our software as necessary. So this software here is a standalone software done for this application. So it started in a more general purpose application, but finally the PhD student decided to do his own thing, and he is a very good programmer. And it's now a tool that is used by a lot of chemists.
Follow-up question. At any intermediate level, do you need a graph representation like the nodes and?
You are questioning whether you need a graphic presentation?
Not graphic, graph representation where you have the information about the molecules and their connections, the bonds.
Sometimes you also have that. Sometimes it's given, sometimes it's not given.
So without the interconnection information, how do you?
But often in many applications it is given, and then we can kind of derive these substructures, and also something that we also have to derive is kind of, so if you have kind of these kind of representations, so this does not represent every single molecule anymore. So if you have certain configurations, you know that these are kind of these bands, and we use a band representation here, or you can switch to these representations, so you get really the van der Waals balls, or here you have a representation that has different balls where the connectivity, so the bonding is explicitly represented by sticks between these atoms. So this is actually pretty much standard, and you see it in a lot of visualization tools. It's a lot of engineering work, and I must really say, so it took some time until we were at a level where we had kind of all these state-of-the-art visualizations represented in this tool. And this is again coming back kind of to telling a story about a collaboration. This is often the case in the beginning of collaborations. Everybody has to be patient. The partner has to be patient, because in the beginning often a lot of engineering is to be done, but also we have to be patient until we finally get to some research questions that are also interesting to us, which is in the end kind of the goal. And now here, following up here, we are getting kind of to more interesting questions for us. So looking here at a small example where we have in the background, we have a part of this large molecule where we are interested in the docking, and we have this little probe where we are interested in where it's docking. For sure, I can go there and I can look at all the time steps and see what is happening. But another possibility is now to kind of create places where this little molecule moves all over the time, and then it gets this big red plop. And looking at this, you can say, okay, this is not very informative. But after a short time, you realize that, yeah, it's not a surprise. This guy is moving, and the other guy is also moving, and they're all over the place all the time. So we need some smarter way to do this. This is taking these molecules, so this is already just a little part of it, select some structures of interest which are used to define a stable frame of reference. And then we do the aggregation just... Yeah.
When you're thinking about displacements, rigid.
No, they are not rigid.
Yeah, so because it's moving, the configuration itself is changing.
Yes.
Of the other part.
Yeah.
Because one part moves, right? So how do you then do the collision detections and stuff in this case?
We do not really do the collision detection, but I come to this point a little bit. So the first step is that we really kind of define here an internal frame of reference that is somehow attached to these things, and then we assume a rigid body transformation, which is not always fulfilled, but I also will come back to that. Just try, to get kind of an optimal representation of this. And then we aggregate in this area, and here you see that you get a much sharper distribution area, and then if you plot in this region this molecule, you really get the area where it is docking. This scales very well also to larger molecules. I give another small example here. So this is a little molecule which is known that it has hydrophobic areas and other areas. And what you see around here is a whole bunch of water molecules. This is just a small part of a huge simulation where we have a lot of these molecules and a lot of water. And here, this is just an aggregation of water around this molecule along over time, over one trajectory. But we also can do an aggregation over all members, all ensemble members here. And then we get a picture like that. So this is just a color map of the probability distribution where water would be around it. And then we get really very sharp hotspots around here. This was nothing new. This is just confirming what they know. And you also can look at it from the side, and you see that kind of these water is building kind of these kind of layers. This has also been known, but there was a lot of excitement seeing it. Nobody had seen it. They never seen it in that form. And since then, so with this collaboration, but every time that I meet him, he shows me a different example. They have been using this tool, and then look here, how nicely you can see this phenomenon or that. So this is our first example again, and here we come back kind of to your question. And if you see here an overlay of all the ensemble members, and you see that the main structure here is pretty consistent, but the small parts of the molecule, you have a lot of variation here, which is probably not so relevant, and you get a very strong area, docking area here, and this is also something that has been known. But we also find kind of a second docking area which has not been known before. And now to get kind of a measure, so for which molecule can we do this procedure? Which molecule has kind of a stable shape? We develop in the next step kind of a shape footprint for all of these molecules. Thinking here, so we have, this is an example of a molecule that changes shape a lot over time. So here we have a very linear behavior. So here it's more planar, and here it's more knot, and it's a spherical shape. We can use kind of just take every of these atoms in one of the molecules and compute the covariance matrix and make an analysis of this matrix to classify kind of every conformation in terms of this shape. And all of the dots that you see here represents one time step. And here you see that the footprint is huge. So you have, during the simulation, you have kind of a lot of times when you have this linear part, but you also have a lot of times where you have a spherical thing. And probably such a molecule is not very appropriate for this approach that I presented before. So here are some examples how this can look like. This is alanine, where we have a kind of shapes all over the place. For DNA, we have a very localized behavior and a linear structure. We have here for catalysts, there's some variations that we see here from linear to more planar. And this is again the amyloid in our main example at the beginning. It's pretty stable. There are some variations. And then it turned out that this is not only a nice measure for us when we can use this. This representation itself.
Linear, planar, spherical. Is it based on certain PCA kind of thing, or?
Yes, exactly. So we are basically looking at all points represented by the atoms. You can use them in a weighted way or non-weighted way, and then just use the covariance matrix. They are kind of then looking at, so I had here kind of in the definition, if you look at the eigenvalues, you see you have some normalization over all eigenvalues, and you have the difference between the eigenvalues here. And this forms a nice barycentric shape. All these measures sum up to 1. This means every shape gets exactly 1 point assigned in this triangle. So this is something that I have kind of stolen from tensor field analysis. We have been doing a lot of work, but this is the standard characterization for tensors. And this is completely new in the domain of chemistry, but they're using it a lot now. Just seeing, getting an idea how stable the shape stays over time.
So what do you have in the top and bottom here?
This one?
So what is there in the top and what's there at the bottom here? Or are they completely different?
Because this is always a spatial representation of the molecule.
Okay.
And if you run the simulation over this molecule, this is kind of the footprint of its shape that it has. So here in this kind, if I run the simulation for this alanine, it will sometimes have this shape. So this is really elongated. And then over the course of the simulation, it will kind of knot together, and then it has this shape. Then it relaxes again, and maybe it gets a more planar shape. And every point here represents kind of 1 time step. And normally we use the intensity that is related from these dots related to time. Here, everything is all over the place. It seems to change the configuration all the time. But sometimes you can also observe that something is starting at the beginning from linear and then very stably rests in another state. So this is the overview of the entire tool. In the meantime, there are a lot of more components that I have not been talking about, but something that really turned out to be essential is kind of this scripting editor, and then we developed a kind of a domain-specific language. Yes, please.
I have again nice question in this
yes.
presentation. So 2 questions. One is what is the docking?
Yeah.
So sorry, I don't work in visualization. I'm qualifying this again. So one way to docking, I believe, was through multiple structural alignment.
Yeah.
I'm saying, so in that case, for structural alignment, I think the algorithms are quite complicated, right? Like DALI and FAST and other things, right? I'm thinking, is there a subroutine in your procedure? Because one of the tasks you have is to do it very quickly.
So there is probably something that's really important to distinguish. We are not doing the simulations. We are getting the results of simulations. These simulations that are shown here, they are partially running for months. And this is an analysis that happens afterward. You're completely right. We are not competing with any chemist simulations. So these simulations are really, really involved. So our using quantum mechanics. They're also developing their own simulation software, partly also using big packages that are available. And then the point is to get as much as possible out of this data that they have been running. Something that you often can see, people are running simulations for months. Then they spend half an hour with the analysis and throw everything away. Just because there is no way to explore this data in full detail. And this is what we get. They are kind of storing the data. This can be large data sets. This can be pretty large. And we load these data sets. And then the exploration should be fast. So the simulation will not be fast. So this is something where we also don't interfere.
Sorry, I'm just there.
Yeah.
Like, so why we are doing the visualization? I mean, is it helping a human expert to know that the docking positions?
So, yes, it's the docking position itself is just the starting point for the next question. For sure, they look at how does a molecule look at this point. Is there something characteristic? Trying to develop some hypothesis. I think this is something that is really interesting in the scientific process. If you are in industry and you are producing things, you don't care. You just want numbers about things are good or bad. But during the process of understanding your data, I think it's really important to have this possibility to really look at it, interact with it, reason about it, to get an idea of what's happening here. So I already see it. I will just get to my second application, but it doesn't matter. So I'm happy if there is about any questions and about any interest about what we are doing.
So since the last thing, the shape thing.
Yeah.
It's right that this is your group which tries to separate shape as a convex combination of.
Yes. There are many different ways to represent shape. But it has been for just these point distributions, this is kind of a very efficient way to get one measure. For sure, there in other contexts, there are a lot of other measures that I will also.
So in that case, those green dots are basically temporal evolution around those on that simplex?
Yeah. So this is where kind of how these, if this is this represents the entire time span. So this means here the shape does not change much. There are little, but this is known. This is a DNA. DNA has a very elongated structure. It moves a little bit, it bends a little bit, but it will not transform a lot. And here we have some transformation, but also not a lot. And here there's much happening. Yes.
Yeah. Do you track how the changes happen over time? So is it like drastic or is it gradual?
Yeah, so you can see it a little bit because you have kind of this encoding of time in terms of color. So here you see that there's no clear trend visible. You might also then go use in the end the entire tool and look kind of at the development over time. And then now I'm interested in what is the shape if this property in this area, and then you only get shown a part of it, and then you could say, okay, if this property is strongly expressed, I typically have a very elongated shape or another shape. So the last comment to this application is there's now a group, so this is not my group itself, that are taking this software and bringing it in the dome for educational purposes. To show kind of some basic structure that all of us know. How does alcohol look like? What is sugar? What are different kinds of sugar? What are the differences? And this is work in progress, but just to show this link to this possibilities that we have in this entire environment. So with this, I come to my second application, where I have much less detail. And many things and concepts are similar. This is a medical application. This was inspired by people who are especially interested in one disease, which is called the irritable bowel syndrome. There you have problems probably related to the brain, but also to the gut. And often it's not really clear where the problems are coming from, but it's obvious that there is some link between the brain and the gut. They often talk of these brain-gut axes. And there's not much known about these diseases, and they are looking all over the place. And this means the data that we have comes from very different modalities, has very different structures. So we have on the one hand side fMRI data, functional activity measurements in the brain. We have some common knowledge like brain atlas, brain regions. We have a lot of questionnaires available where they even ask people about depression and all kind of other things. We have blood samples, and the data is really all over the place. A lot of patients, I think, yeah, a lot here is something different when we're talking about molecules. This might be 200 patients that we have for all these informations. And here is the analysis is normally also done using a lot of different tools, doing statistics with this tool, doing visualization with that tool, and it's really hard to bring these things together. It's very, very time consuming. And so again, as before, the first step was bringing it all together. And so we have a lot of implementation of statistical correlations where you can interact. We have spatial filtering, we have aggregation, we have multivariate filtering, bringing in a lot of different visualizations that are linked together. I want to highlight one of the visualizations. This is again just a picture of the data, which is very frequent in visualizations. This is not magic. This is basically a standard. It's called parallel coordinates, but I still want to explain it because we are using it a lot. It's very convenient for filtering. So every axis here represents one variable, one parameter in our data. So for example, this is the axis for depression. Then we have here maybe a blood measurement, and so on. And every of these lines represents one patient. So if I'm now interested in a specific patient, I can see, yeah, he has the disease. This is just a yes or no question. This is the age. It's rather an older person, and so on. And I can click, yeah, and he also has some depression. And often here you can use this just to get an overview of the data. I'm not so convinced of that, but I use it a lot for interaction.
How do you research the order of the vertical?
Yeah, so the order of the verticals, this is even a known research topic in visualization. So what we have here, it's more or less a random order, but you can, in this application, you can just pick an axis and draw it somewhere else. So if you are specifically interested in correlation between two different variables, you can just change the configuration here. So we use it. You also can kind of easily click on an axis and it will just disappear if it's too much. So you can put it together according to your interests. And then you have kind of these little triangles that can be used to filter. If I move this up a little bit, I remove everything that is below here. And this means you can put very advanced queries to your data just to define groups. And this is what they are using this a lot for, just to define subgroups. And in this case, we have kind of this red and the green subgroup, which they would like to compare in a further context. So here, this.
I didn't fully understand the picture here.
Yeah.
So, HAD depression, right?
Yeah.
So you're able to identify.
This comes from questionnaire. So I mentioned that our data contains questionnaires, and this can be either something that a doctor puts in, the level of depression, but some of these questions are also directly relying on what the patient is saying. So if the patient tells you, I feel very bad recently, they get kind of a scale and they have to say, where would you put your feeling? You might have seen this in context with pain, that doctors try to quantify your pain. So it's subjective. I think
it's a cognitive assessment.
Yeah, I think this data is incredibly complex. It contains so much information. Some of these data is very sure. So if I do a blood measurement, I know most likely more or less exactly. But if I have these questionnaires to the patients, there's a lot of uncertainty in this data. Also, this might be interesting to incorporate here also, but at this point, we didn't care about that. We are just representing the data as it comes to us from these people who are working with, they are partially working in the clinic and partially working more in research, and they have kind of real patients they are looking at.
So this is where I think human in the loop becomes very important.
Yes, I think so. Here, this gives some screenshot of the applications that we have. This was a very long iterative process, and also just the design of these things took a lot of time. And this was inspired by this specific collaboration. This is the report syndrome, but later we extended kind of the set of users to other similar problems also. The only thing that they all have in common is that they are looking at fMRI data. But the additional data can be very differently, and then just the axis here would be a kind of exchange. So these are the axes from the parallel coordinates. Here we have kind of the brain atlas, where people can select something. We have spatial renderings with slices, and also we have volume renderings. And you can use, for example, this to define different groups. You also can select, for example, an axis and ask how is this axis correlated with the activity spectrum in the brain, or you can select something from our brain atlas and I get specific regions, and then you ask how are the activities in these regions correlated with all other measurements that we have here in our data. So this is a short movie, but I will not show it longer. You see a little bit how people interact with these things. You can put a lot of queries and play around with it. We did a formal user study for this tool, and we got the feedback that works, that would have taken weeks, they can now do kind of in half an hour. And I think sometimes I'm not really want to say everything should be fast. In contrast, I think all the reasoning process should take its time. It should take as much time as it needs, but it should not be hindered by switching from one tool to another tool and having a slow technology. But here, having the possibility to get kind of immediate response about what you are looking at. So many of the things that we have in this application were similar as before, and I actually was planning to come back to this at some point, but due to the time, I don't think that we will manage. So especially the question about the patient-specific brain regions has been kind of a technology or method questions that we have been dealing with for quite some time. So the last applications that I wanted to talk about is related to interaction between light and matter. It's again chemistry, it is again molecular simulations, but this time, so it's not so much about the location of the atoms or the molecules, but it's more about the electronic structure that is related to these electrons. And if you excite a molecule, then it releases this energy again in form of light afterwards. In the design of kind of lamps, the design of solar cells, it's kind of important to understand these properties of kind of taking in energy from the molecules and giving it away again. And here are just some examples from really our applications of different materials which have kind of different colors, let's say, light. We're talking about the electron structure. So we have here again a representation of a molecule in the back. These are rather small molecules that we have here. And the plots that you are seeing here, these are isosurfaces showing the density distribution of the probability distribution where an electron might be. You see that you have to select some isovalue, and then you get kind of this representation. And here in this, you have most of the charge localized in this area. You have a little bit here. And after exciting the molecule, there might be some changes. So you see that things have been moving. And while these are kind of very typical representations in chemistry, they're really, really hard to read. You see that there's a difference. But what is the difference? Can we quantify that? Can we get a little bit more objective analysis of these transitions? And one thing that we did here in this application is then computing the segmentation, spatial segmentation related to certain subgroups that are known to play an important role, aggregate the charge there, and then represent the charge in the flow diagram. So this is a state in the beginning, and this is a state in the end. And the color refers here to different groups in the atom and the molecule. I've taken this picture actually from a chemist publication. This is not from our own publication, just to show how interested they were. And this, just this picture here, kind of won the prize for collaborative work in Sweden in the area of chemistry, introducing a completely new way of representing this process. So, very nice. We have here the representation of one molecule, how it is changing. But what is typical, we have a lot of stuff. We do not look at one molecule, but if you design a new molecule, you might be interested in exchanging some of these groups, exchanging individual molecules, and know what is the impact kind of on this electronic transition here. You also do not have only one excited state, you can have several excited states. And this leads in the end that you might have, in our examples, these were in the hundreds of different configurations. And then comparing these things becomes very difficult. Something that I did not mention in the previous slide, I think something that is also very important when doing visualization is kind of this interplay between quantitative measures and visual measures. And what we have here, this is basically, as in this case with 3 subgroups, this is a 3x3 matrix, which represents this entire transition. It's a very concise representation of a very complex data. And it has a property that's understandable. It's understandable by the human being, but it also can be used for automatic methods. Since it's really just can be represented as one vector of numbers. And this is something that we are using here in the following. We are using kind of this matrix here. It can also be larger if you have more subgroups, but mostly the number of subgroups will not exceed kind of 10. And then do just a hierarchical clustering of these groups, and which will result kind of in such a dendrogram representation. A very abstract representation, probably we cannot much do with it. So therefore, we just decided to augment this dendrogram with more information, and for this we developed kind of different abstraction levels of this representation of groups now of these transition diagrams. So this is basically the transition diagram as we had it before, just here representing kind of the mean of a group. Here we have an extended diagram where we also express kind of the variance of all these entities. And this is really boiling everything down just to one color, which is a trace of the matrix, which gives a good measure for locality, how local this excitation will take place. And this is something intermediate where we just focus on the dominant groups. And then we can use this representation to augment our dendrogram here, and gives us a first overview what's happened. So you see on the leaves here, which are our ensemble members, kind of get a very quick view what is the type of the charge transport, and then you can see here summaries of the group on different layers. So this is just a hand-drawn sketch. But if you are looking at kind of how this looks in real, this is kind of a result of a real ensemble simulation. And as before, I think this is a repeating pattern. We will have here parallel coordinates showing additional quantities. Sure. Showing additional quantities, and you can uses to explore. This is just a dimensionality reduction plot which shows the distribution of all our ensemble members. Here is a representation of the major clusters, and something that can never be missing is the inspection of the individual parts. So I guess we have to jump over the method part completely. But so this is my intermediate summary actually from the talk, and where we see we have in all applications we had a lot of things in common. So we have spatial renderings, which are often familiar, that people are often familiar with. They use they have statistical plots, they use filters, selection, and interaction in various layouts and combinations. For all these things, that's very important to be efficient, to think about design, to talk to the user. But there are also some things that are, so there are some things, yeah, very application specific questions to figure out what are interesting features, what are interesting quantitative measures, which is a very sensitive question, what are relevant tasks, and how do we design the interface. From the method point of view, you might also have seen there have been some recurring questions. We again have, so how do we define the features? We have features actually on both sides. Here, this is more from a mathematical point of view. How can we capture something like a feature in a semantic way? On the one side, where people say, my feature, this is an electronic cloud. How can we make this precise? How can we make something measurable, quantitative out of it, that we can further use in automatic processes? What is good segmentations? How can we use compute them accurately, reliably, and efficiently? How can we cluster on the comparison tracking? This is a recurring task that we have. And for all these things to be acceptable in our application, it's important to be reliable, to be robust, to be understandable. If there's something too much magic involved, people will reject what they see. Yeah, in the second part, I wanted to talk about comparison and tracking and using topological methods, which is actually a huge part of my research. But I will skip this now completely. But anyways, I think I'm very happy to see that there was interest in these application areas. It tells a lot about the process, how we are working in visualization with the application domains. So we had already a lot of questions, but if there are more, so I'm happy to answer anything.
Thank you, Ingrid.
I had one question. So if you're looking for something very specific from a massive data set, and the data set is so massive that looking at the entire data set, massive data set itself feasible, but you precisely know what you are looking for. So is it possible to have?
Yeah, I think it's not trivial for sure. You have to design your application for that. And in many cases, applications are designed that you somehow can load your data set, but we have also some applications where you can stream things. But the question of interactivity for sure becomes harder. So if my data set has to be streamed for the analysis, I have to think about kind of loading data continuously, and this just takes time. One alternative here, so and this also depends on what kind of data you have, but for example, for simulations, and this is something that we are also doing, especially for climate simulations, these data sets are so big they cannot even be really stored. So they only store parts of the data set in time steps which are often very, very far apart. What we are currently working on is bringing some of these analysis methods directly into simulation, which is often called an in situ visualization. It's not really visual at that point. It's more an in situ analysis for good visualization afterwards. But we try to have simultaneously with the simulation run also some analysis tasks which are extracting some information that might be of interest afterwards. For sure, we have to have some ideas in which directions the questions are going so that we can design these things. But there are some generic things that appear in this analysis again and again. And then try to export this in a very concise way, which allows us later to get a more interactive, efficient analysis. But this is definitely a very good question.
Yeah. So beyond that, so if I'm very clear what I'm looking for, and then there are certain parts of the data set which are very relevant to what I'm looking for. So is it possible to integrate the visualization process with a learning algorithm which will actually look for only those aspects of the data set which will have some relevance to what I'm looking for?
Yeah, people are working on this. This is not my area of visualization, but AI for visualization and visualization for AI involving this is a very, very hot topic in the community. So that people try to get representations of this process, use it to highlight specific regions that have been, for example, important in a classifier.
Yeah, I think in the area of visual analytics is where in building systems that incorporate. Any questions?
So if anybody has more questions or something is coming up, so I will be here the next month. I'm sitting around here in the hallway most of the day, and I'm always happy for everybody who comes by to discuss.
I have one quick question because if there are other questions from the audience, we'd be happy to give you preference. But if you're thinking about one, yes. Yeah.
So just a general question about. It looks like basically you come up with different ways of visualizing your data and communicating things to, which we all do in papers that we write, and so I mean, are there kind of new new ways, like different kinds of graphs, or like that? I mean, do you come up with new like a graphical way of showing data?
Yes, so for sure there are certain patterns that appear again and again, and you're right, everybody is using visualization every day. There's no paper without visualizations. Partially due to previous work from the community, partially things are pretty obvious and so on. For sure, we are also working on developing novel visual encodings, sometimes like this transition diagram. Sometimes we are reusing, for sure, certain concepts in different areas and different things. But I think altogether, this visual is the last step. There's so much of analysis before kind of to I think what do we show as important and how. But both things are new. Yeah. I mean.
So my question was kind of related to that, and maybe it will help. So you talked about the transition diagrams, right?
Yes.
Which was a very nice way of for the chemist to understand the way the electrons, the transitions indeed happen. It summarized a lot of information. So there was, I'm sure there were a lot of iterations that went into the design of that diagram.
Yes.
So contrast to the parallel coordinates representation from the other applications, the brain study application, where the representation is known, but how do you interact? The kind of interaction would have gone through some iterations before deciding on kind of a workflow that will work for the particular application. Can you talk a little bit about the design of the visual representation and the design of those interactions? Like how do you go from start till the very end?
I try. So there are some people who are doing this in a very structured way. They meet the application people, they come up with a questionnaire, ask them tasks. So for us, it doesn't work like this. Often it's very, very unclear where these things are going. For example, for this application, there was a previous other applications that we had with physicists where we were actually using topological methods for the analysis of electron density fields in crystal structures. And I presented this idea at a meeting with physicists, chemists, and so on. And then there was this one chemist saying, "Oh my God, this is naive." I was really, really shocked hearing this. Why the physicists were quite happy with what they saw. And then there comes this chemist and said, "Oh my God, this is naive." And I said afterwards, this is actually one of our partners for this new project. I went to him and said, so I want to understand why. What is happening here? And we were sitting together and discussing these things. And then it turned out that due to the different applications, certain aspects that are very important for the chemists are not important for the physicists. And he's a very open-minded person, so he can be very provocative, but also then, and we were discussing about these things. And then somebody had the idea, maybe we could make an experiment in this direction. Maybe something similar could be interesting in this case. And the chemist was, yeah, maybe not. And so we started his first prototypes. We were looking into it. We had a lot of meetings. And then all of a sudden, he became very enthusiastic. And then so he himself was not so much involved, but another chemist at that part. And he's even now in our group. And he comes in every day, looks over the shoulders of the people, and we have discussions. And then there are these times where I start reading chemist papers, trying to understand what is behind that, coming back. So for the specific diagram, there have been a couple of prototypes that we have been using, and somehow it started to converge against representation in this form. So unfortunately, I cannot tell so that we had kind of this structured approach that is always kind of preached by visualization people. But I think if you are really in a scientific domain, really integrated in their research, figuring out what is the task is already part of the research. Figuring out what you are looking for. So maybe it's even after using this tool, you will never use it again because now you know how it works. Now I'm happy with my one number that I can feed into my classifier. But to get there, there's a lot of, I think, playing around with the data, a lot of communication is just necessary. And as a remark for this application, so I think there are so many more things to do, and there we even have a collaboration with BJ going on, and with more where we are looking onto the data from a different perspective as a bivariate analysis, and I think there's a lot more to do. But this is the nice thing, how I measure my success. Some people have kind of these big user studies, is if I see that this software is kind of given from chemist to chemist, and they use it, and you see kind of these presentations in chemists' publications, which is for us a big satisfaction. Yeah.
Yes. So I think that's a very interaction. You interact with many scientists or many application domains, but many of them come with different intents. One might be for communication, one might be for exploration. So, like from your experience, what's the kind of various?
I'm mostly interested in the aspect of understanding of data. A little bit in communication also, because we have this link to the museum. So I think this scientific storytelling is also something that I'm interested in. But there I'm more as a consultant, kind of in terms of scientific transfer. And then often these actions are given to some engineers, which basically make it safe that you can put it in a public environment where 5 kids at the same time are playing around with a big interaction table. And also we have some pedagogues that are coming in there, kind of trying to limit the possibilities of interaction in public spaces and all these things. And for sure, also it comes down to generate pictures for publications, which should also be a possible with our things. But visualization really, as you mentioned, has so many different aspects. There are a lot of people in visualization who have targeting very different goals. So for me, I have a physics background, so I really am also interested a lot in the science itself. For me, it's just exciting to work with these people. And I think sometimes it's such a privilege that I can pick my collaboration partners, and I do not only pick them in terms of interesting topics, I pick them in terms of interesting people. I think picking people who are open-minded, who really want to do something new, which is just going beyond, could you please implement this cool software into my framework? This is not of interest to us. So that we can try to reach something new jointly. And me, I'm not the expert. I'm allowed to ask all these stupid questions. I get to know all these wonderful people who know a lot about medicine, neuroscience, physics, chemistry, and you can kind of participate in these top-notch where really science happens and try to complete something. Sometimes I consider us also as interpreter, kind of in translating semantic science question into some data problems. And I also love this part where we do really core technology development, where we try to find novel methods to get very algorithmic. So I think this is something that I also like. But also since I play, I think it's very nice.
Yeah, so with that note on how the visualization, where the analysis is with an interesting collaborator, human in the loop, right? Yeah. That makes the whole process pleasurable. So yes. Let's thank Ingrid again. We have a small memento for that.
I have to present it to you. Let me read it out. Presented to Professor Ingrid Hotz for delivering the CSA Distinguished Lecture, January 13, 2023, from the Department of Computer Science and Automation, IISc. So with great pleasure.
So, if anybody wants me to talk somewhere else, so I'm happy because that's why I'm here.
Thank you so much.
Yeah.
So maybe I will also get a picture taken. This is something else from the department. Oh. Yeah, that's another souvenir. Right. Yeah, sure. Thanks everyone for coming.
Thank you for coming.
Oh yes, sorry.